Viscoelasticity, and it's my privilege to be the chairman of this plenary section. It is my pleasure to introduce our first speaker, Professor Patrick Le Tallec, Professor of Mechanics at École Polytechnique Paris. Professor Patrick Le Tallec field of research is concerned with computational mechanics. A part of his career is devoted to augmented Lagrangian and operator splitting methods in nonlinear mechanics, to the numerical analysis and simulation of nonlinear elastic problems, to domain decomposition techniques, and to fluid structure iteration problems. His current interest concerns the multiscale and multiple contact of nonlinear structures, such as decomposition techniques for large problems with advanced modeling of elastomers using continuous transition from mesoscopic to macroscopic scales, or the study of multi-layer system in hypervelocity regimes. Professor Tallec holds a PhD from the University of Texas and the University of Paris. He has co-authored 7 books and is the author of many outstanding papers. He has a long-time collaborator with industrial companies such as Michelin, Dassault Aviation, or Peugeot. He is the editor of the International Journal of Numeric Methods in Engineering. The title of his lecture is there, and Professor Le Tallec, the floor is yours.
Thank you very much, Professor Suarez. And I would first like to thank the organizers, the organizing committee, for their very impressive invitation. I would like to take this opportunity to bring you along a path that we have followed with many friends and colleagues, from the youngest being Antoine Gloria at Brussels, probably you might say the older collaborator being Marina Vidrascu at INRIA, with many colleagues at Michelin and with colleagues at Polytechnique. And the path goes about the modeling of polymer structures. So polymers, why do we want to look at polymers from an engineering point of view? Of course, because they are in many applications, one of them being of particular interest for me and some of my friends. But you also have many more recent and challenging applications in protection, like in nuclear industry, shock absorbers, and aerospace. And in those applications, they are put to very severe regimes with large deformation, time variations of the loads, rather aggressive environmental loads. And despite that, you are asked them to perform efficiently with minimal amount of matter and quite reliable. You want them to be reliable. So that's the engineering challenge. From a scientist, a polymer is interesting because, first, of the mechanical models that it requires to handle, going from large deformation elasticity, but adding, evolving anisotropy, aging, viscosity, crystallization, or damage. Of course, next interest is it has built in a lot of structural instabilities that you must cope, provoke, or accept. It is multi-scale by construction, because the polymer in itself, polymer structure, have fiber reinforcement, they have fillers, they are made of network of monometric structure with chemical bonds, etc. And polymers are also very active, let's say, in multiphysics field, like magnetorheology, to get active structure made of magnetorheologic polymers, like crystallization, wetting, polymer gel, etc. So that's roughly the scope of interest of polymers. So the past starts with hyperelasticity, and it starts with Tinsley-Oden in 1978 in Texas. And hyperelasticity is a simple case where the stress tensor, written in the reference configuration because of a large deformation, derives from the free energy and is only a function of the dilatation tensor, or equivalently to the Green Lagrange strain tensor. So you have a very simple mathematical expression of the constitutive law, although, of course, and we will see that later, it's always a challenge to find the right form of the specific free energy and the right coefficient that you should use in order to cover the largest deformation regime that you must face. But from a mathematical point of view, the situation is rather nice. It's set in a minimization problem. You minimize the energy, total energy, on a set weakly closed in a nice Topolev space, and the energy itself is weakly lower semi-continuous. And it is weakly lower semi-continuous. That means that you have existence by the Weierstrass theorem. And it is weakly lower semi-continuous in many situations because of the polyconvexity of the free energy, because of the convexity of the energy as function of the gradient, the cofactor, and the determinant. So existence, at least as a minimizer, is rather well understood. You do not have existence of the Lagrange equation, but you have existence of a minimizer. Something which is also well understood, that you have because of the nonlinearity, you have a non-unique solution, which means that because of non-uniqueness, you will be faced with buckling. So that will be challenging for the nonlinear solver. You must have a nonlinear solver which can detect buckling, we can predict post-buckling, and part of the interesting thing is if you want to develop a stability analysis, you should be able to do that on a multi-scale level, and that's what we have done a few years ago with Eric Lignon and Nick Triantafidelis using a block wave expansion to have a two-scale analysis, stability analysis of this reinforced ply in bending and a comparison between the numerical analysis and the numerical prediction. Okay, so there is still work doing that on the nonlinear solver going, but this is not the main part of the path. I say that most of the work has been carried on to industry, and with a bit of knowledge and know-how, they know how to handle that. Now, the next point in the path, the slope is getting steeper. The next slope part is viscoelasticity and time dependence. So polymers evolved in time. So there are damage effects that you can, the first one is the Mulling's effect, so reorganization of the chains at the first loading. This can be ignored in many situations if the polymer is properly prepared by cyclic preloading before used. But in any case, they will show relaxation and they will show dissipation. And in fact, they are used for the dissipation properties. And there, the situation comes a bit more interesting. The historic path for handling dissipation in large deformation is to use an additive decomposition of stress, that is to use the so-called added stress. So stress will be an elastic one plus an extra stress due to dissipation. And the extra stress is governed by some kind of Dapshot rheological model, which leads you to a differential constitutive equation governing this extra stress here in reference configuration or in polymer liquids in present configuration. This model is quite popular. is very interesting for engineers because the coefficient in the law can be easily related to simple experiments like DMA, like dynamic shear analysis. Problem that you may face thermodynamical instabilities. There is no guarantee, because of the time delay in the stress, that you will satisfy the second law of thermodynamics. And there is a numerical evidence recently pointed by Sanjay Govinji on a fastly rotating wheel, where you can at least suspect that this model, when you have large, fast rotation of the configuration, may lead to thermodynamic inconsistencies, that is, a violation of the second law of dynamics. That is, you will create energy if you are at constant temperature, which will be nice, but normally it doesn't work. So the right direction in the past probably is to use the direction of Mendel and Siderov in the 80s that we have used also with Christophe Rayet in the 80s, that Sanjay Govinji and Stephanie Rees have also used. It is to base the theory not on the additive decomposition of the stress, but on a multiplicative decomposition of the strain. That is, that in large deformations, the dilatation should be a product of an elastic deformation and a viscoplastic deformation. Observe that this problem, if you're losing anisotropic bodies, this product is not exactly, you must be careful with the formulation of this product in order to get the right conservation of anisotropy in those cases. But apart from this little technicality for anisotropic materials, situation then is quite simple. You have an additional internal variable, which is the plastic strain rate, and you explicitly try to identify the dissipation in any evolution. And once you do that by postulating some kind of dissipation law, and once you do that, you have automatically the evolution law on the additional internal variable, which will guarantee this type of dissipation. So it's really a dissipation control evolution law that you can build. And then the idea is to find the right form of the dissipation here. So this structure is very similar to the structure that you get in viscoplasticity in small strains. That means that you have, even in quasi-static simulation, you have an ordinary differential equation in time at each point governing the evolution of the internal variable, coupled to your partial differential equation, which governs the conservation of linear momentum. The slight difficulty is that time enters the picture, so the notion of steady solution does not exist anymore. You either have, in polymeric structure, time periodic structures, when you have a rotating body, or you have initial value, boundary value data, like for example in biology, when you perform a surgery on an eye and you want to know the evolution of the shape of the eye during this evolution. Okay, so you have to live with that, that is to identify proper time conditions for the proper problem. From the numerical point of view, the strategy used more generally, that we favor in particular, is use time discretization of the problem and a local elimination, because of the constitutive law of differential equation, the local elimination of the internal variable, so that you can reduce the problem to an hyperelastic problem after this algebraic local elimination. Now, there might be some variance here. In particular, if you want your evolution of the internal variable to be less sensitive to discretization noise, you may wish to use a continuous, piecewise continuous, like Sanjay Govinji does, a piecewise continuous discretization of the internal variable, which will then lead you to a three-field problem, which will be more expensive to solve, but which may lead you to more stable and regular fields in certain situations. Now, this game can be generalized and is generalized in the present Congress to many different situations. First situation, you can properly treat thermal coupling and the thermal heating, for example, of a tie, because you have direct control on the mechanical dissipation. The next thing is, because you have the second law and the first principle, you can complexify the problem to introduce additional variables, like in magnetorheological elastomers with Nick Triantafidelis and Kostas Danas, like other multiphysics that I've seen with Christian Lander yesterday. The treatment will be always roughly the same. You add a new phenomena, you add a new variable, you try to identify free energy and potential, and derive the corresponding equation. This is a very nice game, but this is an endless game. This is an endless game because at a certain time, you find a new experiment, you want to be more accurate on a given experiment, so you want to introduce a new phenomena, okay? You introduce a new macroscopic variable, okay? That means that you introduce a new constitutive law. That means that you must identify new coefficients, and the game never ends. So at a certain point, it might be interesting, instead of staying at the macroscopic scales and working with complex physics, it might be interested to go downscale, to go at the network level, and to use simpler physics, but the most complex, most, let's say, relevant microstructures. And that will be the path that we will now follow, and that has been followed in the recent, let's say, 10 years with some success. So why can we do that? The path actually was originated from the early 1940s by the Fleury and Treloar. We had this interpretation, but was not very efficient as a numerical simulation. So the underlying idea is the interpretation of an elastomer. An elastomer at the network level is a succession of polymeric chains which oscillate in a gel, let's say, like in a gel, and which through vulcanization are connected through chemical bonds at certain points at every L0 length. So for the typical length is 10 nanometers. So you have this microstructure of the network, so you can derive a thermodynamical model of this structure. Chains characterized by the position of the chemical bonds and characterized by the local orientation of each individual monomers. Now, this description is too rich, is untractable. So a simplification that is done then is to say that the monomers can have a very free motion, and the links, they move very slowly because of constraints. So you make a time scale splitting, assuming that the monomers are in thermal equilibrium, and that the links, the nodes, roughly at zero temperature, or at very small temperature. You also cheat a bit by treating the excluding volumic energy, that is the fact that two atoms cannot be at the same place, by adding that as a volumic constraint directly at the junction level. If you play this game, which is the initial game of Fleury and Treloar, you arrive to a local free energy which has this aspect. You see it's only a function of the position of the junction. You have here the thermalization of the different monomer links, which give you a Boltzmann-Gibbs distribution of the orientation, from which you deduce the free energy of the given chain, constrained by the position of the end lengths. And you arrive to this expression, or any simplification, where theta is the inverse Langevin function. This is a micro energy, and to go to the macroscopic free energy, you play the game of minimizing the local free energy with respect to the local position of the junction with imposed macroscopic boundary deformation far away at the limit of the representative volume element. So how can you implement that? We can make it brute force, like we have recently done with Antoine Gloria and Marina Vidascu, trying to find the numerical minimization of the network energy, at least to see what you obtain. Or you can use approximate minimization. Brute force, well, you generate randomly a network of nodes. You construct a Delaunay grid of the network in order to have connection between different nodes, local connection between different nodes. They give you this type of figures. And on these figures, you remove some edges in order to control the functionality of the network, that is the amount of edges which is active at a given node. You arrive to a simulation, a geometrical representation of the network, and you perform energy minimization on this, which is a finite element model where you have chain energy on the edge and volumic energy inside the element. What is nice about this approximation is that it has a limit. You can prove that Antoine did prove that when the size of the sample goes to infinity, this converges to a density of macroscopic density of energy. Gamma convergence means that convergence in energy and weak convergence in solution. The stress that you get in this stochastic project has a very small variance, and the limit solution is hyperelastic, isotropic, and it is weakly lower semi-continuous. That means that even if it might not be polyconvex, it has the right regularity in order to lead to well-posed problem. That from the mathematical. And for the physical friends, this approach gives you another back information which has been explored very recently in Paris, where you can, if you know the structure of the network, you can reconstruct a neutron scattering pattern, that is, try to predict what will be the scattering of a neutron wave arriving on the surface. And you can calculate such a pattern from the position, simple through Fourier transform, and predict a different pattern, like observed in this observation, if this one is a total, and this one is a difference between the numerical, the one obtained by full minimization, and the one which will be obtained using the affine assumption. So you get some insight. Affine assumption, why is it interesting to compare to it? Because the affine assumption was the first one which was used by Treloar. In order to compute the energy, he simply said that the position of the links should follow the macroscopic motion. That means be piecewise linear variation at the scale of the sample. With that, you get an explicit analytical expression of the free energy, an integral form, which was further simplified in order to carry the integration at first order, but which could be used at any order if you want to have a stiffer, if you have to have a more realistic energy. Okay, this is interesting, but it's very stiff because the minimizer is very, very approximate. There is another approach which has been followed by Christian Linder recently, where you simplify the network and simply saying that there's only one type of chain, and the chain in a given direction will only have one physical state. And the constraint that you have, you say that in average, the maximal path advance, that is the path which goes in right direction, optimally in one direction, the long maximal path advance, in average, should follow the macroscopic motion. With that, the energy is a convex minimization on unit sphere with global linear constraint, and give you an integral form, a non-explicit, but somewhat more tractable than the ones that we have used in full minimization. And to complete the picture, I should quote the well-known simplification done by Arruda and Boyce, where instead of minimizing on a real network, they have introduced an heuristic 8-chain network and use the energy from this network. How do the models compare in elasticity? Rather well, up till to 300%. Well, Trello are a bit too stiff, but variational and Arruda Boyce are quite good. Experimental also. And you get large deformation on transverse stresses and on large deviation on transverse stresses and on axial stresses in large deformation. What you also observed here is that the network connectivity, the functionality, is a dominating factor in the definition of the elasticity of this structure. Okay. But this idea of network insight, which gives you some better understanding of the physical law and of the local behavior of the structure, can be followed if you want to add the physics that I talked to you about before. That is, if you want to introduce dissipation and damage. And that's a game or an idea which has been followed by Christian Mieux in 2004, by Julie Diani, Stéphane Roux, and Mathias Brieux in 2011. The idea is you take the same assumption which was used later by Christian Linde. No thermal motion of the junction, so no, zero temperature junction, one chain. In each orientation, a chain has a given physical state. But well, the directional elongation, you may assume it's affine, but you add an internal variable on each direction. So that gives you this type of picture. This is the structure, this is your material point. At the material point, you have a collection of directions, and on each direction, you have a mechanical system. And for example, the damage law of Diani, Brieux, and Vacheron in 2006 was simply to control the number of segments, the number of chains in the direct direction, and thus the number of segments in the given direction by the maximal elongation obtains the same direction. So if you had a long elongation, at some time you break chains. And the chains get longer, so you have less chains, which are longer than softer, so you get a softer thing. So that's a very simple thing, and this has been used at this company and gives very interesting and very reliable results at the cracked tip. So we have decided to follow recently the same path for crystallization with Joachim Guillet, who now works at Michelin, and Tien Hanley, one of my young colleagues at the lab. So crystallization, what it is, natural rubber, when they are subjected to large elongation, they tend to crystallize, to form crystallites. They are no longer amorphous. You have very small crystallites forming. And this is very interesting because before of crystallization, the crack propagation gets more difficult. So it gives a much better resistance to fatigue to a given tire because of this additional crystallization. So this is one reason why you have natural rubber in some tires. So our objective was then to model this strain-induced crystallization and to study that in crack driving force on global structural response, situation where the situation is very, very anisotropic. You have very strong variation on loads depending on the orientation. The problem then is that you have to reproduce some physical foundation of this crystallization to respect the second law, to be rather predictive, but not too complex. So the experiments which are done, which are quite tricky because to measure crystallinity, you must go through neutron diffraction apparatus, well, you must make some experiments by freezing the sample, and the temperature might change, so it's quite tricky. But anyhow, what you cyclic loading with crystallization, what you observe is at a certain point here in loading, you have a stress relaxation, crystals begin to appear, so you get a softer curve, then later there is stiffening because of crystallization, and you arrive to a maximal load. After that, in unloading, you unload on this curve with faster stress relaxation and larger number of crystallites in unloading. So this is one first observation that we want to recover, this hysteretic way of loading and unloading. Something that you can also observe in diffraction is that the crystallites are not perfectly aligned. On the diffraction, you can see a certain dispersion of the crystallization alignment with a maximal load. That's also something that we would like at least to explain. So, based on this ambition, we have simply followed the microsphere approach. So, construct 1D chain with crystallization, introduce in this chain the chain crystallization as a local internal variable, construct the chain free energy, and identify the dissipation at this level, which might be questionable, but which is rather simple, and go through a microsphere approach to a full global model. So, for the free energy, use the same model as Christian Mieux with the chain energy and with the tube, except that you assume that crystallization will freeze part of the chain. The chain which is crystallized, it will not move. So that means that the active part of the chain is the remaining part of the chain. So that means that you have less chain to less degrees of freedom to make the elongation. That means that the real elongation is not the total elongation, but that the total elongation, which is part which is frozen by crystallization. You must add network hardening energy because of this stiffening due to crystallized inelasticity. And you must also, no, that's here, and you must also add some energy of explaining the fact that you have a new morphology which has been added. So altogether, you have this type of free energy, the chain energy, the morphology energy, and the additional stiffening. And in the frame energy, we have had some penalization in order to control the fact that the crystallization cannot be negative and cannot be larger than a given threshold, which is physically admitted in most cases. Free energy, then thermodynamic force, derivation of free energy with respect to internal variable, must control the entropy dissipation, so that the variation internal variable multiplied by the force. If you see that, simple way to satisfy, it says that to have fusion, I must be at equilibrium. So first evolution, that decrease of crystallization only occurs at equilibrium where the thermodynamic force is 0. Then you satisfy entropy. In crystallization, since we have seen a delay in the way the crystallized appear, we have had some kind of, plastic type yield. The crystallization will only occur if the force is sufficiently large. And you can add to that, if you want to have a smooth transition between out of equilibrium crystallization and equilibrium transition, you can add a time scale used through a viscoplastic regularization. Altogether, let's give you a 1D problem like that. And to go to 3D, you make the integral on direction of the free energy. You assume affine elongation for the time being, and you use on each independent direction the evolution equations that you have derived from the free energy and the local dissipation. That means that you have one separate history on each direction, which means that you will create anisotropy as you wish next to the crack tip. Number of direction, 50 to 277, which is a magic number for integration on a sphere. Result, this is a result on, so we have used a quadratic chain free energy, so it's very simple physics, local, affine microsphere. We have optimized a constant, that is, we have so that the position of this point would be satisfied. And this is a comparison on a uniaxial traction between experiment and the model. And you can see that this would be the elastic law. So this is the loading, and this is the unloading, with only the two constants, and with a very, very poor, in fact, chain energy. On crystallinity, you get also quite reasonable curves with this model, same simplified model. If you go on local disorientation, that is the amount of dispersion, that you see, you may have 10 degrees where you have a dispersion of crystallization compared to the local things. Okay, the tendency is there. We are a bit too poor in physics to be at that level of microscopic crystallite structure. But still, there is a nice tendency. Then, a problem simulation of a crack. So this is a PS cracked specimen, which is used in many dimensioning experiments. So you have a crack there, a few millimeter crack, put in traction. Because of the traction, the crack will open. There will be crystallization at the crack tip. So that's the deformation and the evolution of crystallization if you make a fast single loading. So you see that in that situation, the amount of crystallization because of the retardation that you have had through plasticity is not so large. Now, if you go to a cyclic loading, which is a bit slower, although it doesn't look on the movie, you see larger crystallization evolution. So that's the deformation of the crack tip. You can see a very mustache-like deformation there, which is very close to real experiments that you have with crystallization, and you have this oscillation. You can compare the different, the effect of the rate dependence on the amount of crystallization, depending on the time scale on which you work. This is an equilibrium calculation. This is a purely plastic calculation. You can compare the amount of crystallized zone with experiments, which fits rather well. You can predict the evolution of crystallinity in fatigue loading with a slow increase of the crystallization as life goes on. And you can also get information on the direction of the crystallite, at least of your image of the crystallite locally at the crack tip. So this is a view from the bottom. On the top half of the crack tip, you have the intensity is the amount of crystallization, and this shows in which direction the crystallization is maximum. You see that obviously it's maximum in the direction of traction, but it's quite large next to the crack tip. As far as if you go further, the crystallization is much more aligned and much more unidirectional. So you have a large variation of anisotropy from one point to another, which advocates in a way the fact that you must use some kind of directionality and some kind of microsphere model in that level. So, conclusion. So in the past, there have been 3 steps. The macroscopic step, let us say that you have an industrial maturity there, provided that you are good on nonlinear solver, that you are rather good in finite elements in order to avoid locking, and that you avoid inconsistent thermodynamical model. To my feeling, the exciting developments are in upscaling, and there have been quite interesting results which are validated by macroscopic experiments on the free energy structure, the shape and the distribution of the microstructure with the neutron scattering effect, the anisotropic damage, or the local crystallization. Now, of course, if you talk to a chemist, he will say your model is no good because you may see this and this and this. So indeed, there is some progress to do. If you want to do a finer match, although the match is also already pretty good, but if you want even a finer match, you must improve your local description. The first thing that you must improve is the model is the affine assumption, which is, we know it's too rough. And the second thing will be to couple in the dissipation different directions together in order to have a more three-dimensional picture of the local crystallization. But of course, this is work to be done by the young people at the end, and so I will close the talk now.
Very much, Professor Le Tallec, for this excellent and interesting presentation. I think you have got 2 minutes, so I can allow 1 or 2 questions. I know you don't have the ideal situation, but if you ask any questions, please stand up so we can see. Okay. Can you...
You have stiffening. Well, experimentally, you can see stiffening, so you have, because it stiffens, you have multiple branching. So the explanation is due to elastic stiffening, which will increase the rate, I mean the G coefficient in the crack analysis. So the better fatigue properties are due to the elastic stiffening due to crystallization. So that's the end part of the curve that you must have.
I will leave. Okay. I pass to you and I will leave. Okay.
Yes. I mean, then there is no criteria on the crack advance. So we have not done a fracture theory relating the way the crack will advance to the local thermodynamic state. You're right.
Okay.
This, for the moment, is very qualitative. We have explained that next to the crack, there is crystallite, there is stiffening. The stiffening is a certain direction. You can, because of the direction of stiffening, in fact, you can still align the direction of the crystallite with the direction of crack propagation, which are observed experimentally. So there is a correlation, but we cannot interpret yet.
Okay. Okay, thank you very much. Yeah.
What do you mean strain localization?
Okay.
Yes? Yes, but that we have.
Oh.
With the affine motion?
Okay, thank you very much. I must close the discussion.
You're
Thank
right.
you very much, Professor Tallec.